Assalamu alaikum beta. Now this is paper 9701, paper 4, 42 February March 2021. So this is the most recent P4 we have, and I just got this paper today from one of my students. So I thought maybe I just solve this paper. All right, so let's start the paper. Now the first question we have in this paper is the most common oxidation states of cobalt are +2 and +3. Complete the electron configuration of the following free ions. So we have to write the configuration of cobalt +2 and cobalt +3. And cobalt, as you can see from periodic table, the atomic number for cobalt is 27. Right, this is 27. So cobalt +2, we already have argon mentioned here, so that means 18 electrons are already been filled. Now 2 electrons will move into 4s, and then we have 7 electrons in 3d, but because it is +2, so that means 4s would be empty. Electrons will move from 4s, and 3d would have 7 electrons, right? And in case of cobalt +3, 4s would be empty, and we have 3d 6. So if you don't like you can skip 4s, right? So this is the electron configuration for cobalt +2 and cobalt +3. Now the next question is CO +2 and CO +3 both form complexes with EDTA4. This is the ligand, we have EDTA4. So cobalt +2 and +3, they both form complex with this ligand, and we have 4 half equations mentioned with the E0 values as well. So use the data in the table to predict what happens. Use the data in the table to predict what happens if anything, like if the reaction is happening. If no, then you can just simply say that nothing would happen. So when separate aqueous solutions of CO +3 and this complex are left to stand in the air, right? So we have what we have here is that we have separate aqueous solutions of cobalt +3 and this complex of cobalt with EDTA, and they are left to stand in the air. And what we have to do is by looking at this table, we have to predict what would happen when a separate sample of cobalt 3 would be left in the air, and when a separate sample of this complex would be left in air. So when we left this cobalt +3 in air, now we have this equation for cobalt +3. All right, and in this like if we just simply let cobalt +3 left stand in air, it will react with the oxygen present in air depending on the E0 values. So based on their E0 values, we have to decide whether the reaction would occur or not. So as you can see that the E0 value for cobalt +3 is 1.82, right? And the E0 value for oxygen to move into water or to gain electron is +1.23. So that means if cobalt +3 would left to stand in air, it will react with the oxygen present in air, and it will be reduced because the E0 value is E0 value for CO3 plus CO2 plus L is greater or more positive. This is more positive, so we can say that the reaction would occur, and what would happen is CO +3 will be reduced to CO +2 as its E0 value as its E0 value is more positive, right? Then next, aqueous solution of this complex. So as you can see that the E0 value for the complex is +0.38, which is less positive than the E0 value for oxygen. So this is less positive. So that means when this complex would left to stand in air, nothing would happen. It will not be reduced into this complex, no, because the E0 value is less positive than the E0 value for oxygen. So nothing would happen. Nothing would happen. ठीक है जी, no reaction. All right. Now next question is hydrated cobalt 2 nitrate. Hydrated cobalt 2 nitrate, this is hydrated cobalt 2 nitrate, is a red solid that behaves like hydrated magnesium nitrate when heated, right? Describe in detail what you would expect to observe when crystals of this hydrated cobalt 2 nitrate are heated in a boiling tube gently at first and then more strongly. So we just have to heat this hydrated cobalt 2 nitrate. So the formula is CONO3.6H2O. First we have to heat it gently. So when we heat it gently, the water of crystallization would get lost. So we get CONO3 2 plus 6H2O. So we can say that it would get, the water of crystallization would be lost. It converted into anhydrous salt. Anhydrous salt. ठीक है जी. And the red solid would disappear. Next, on heating it more strongly, as they're saying that it behaves like magnesium nitrate, and magnesium nitrate is a nitrate of group 2 which decomposes into metal oxide, nitrogen dioxide and oxygen. So when cobalt nitrate, this is cobalt nitrate. So when cobalt nitrate is heated more strongly, it will be decomposed into cobalt oxide plus nitrogen dioxide plus oxygen, and we would observe brown fumes. Right? Now, in the next question, explain why the thermal stability of group 2 nitrates increases down the group. So I hope everyone knows the answer for this, because the increase in the cationic radius, there would be less ion polarization, less ion polarization, and when there is less ion polarization, that means more ionic character, right? And as the ionic character increases, more ionic character, and as ionic character increases, the compounds get more thermally stable. All right. Now, question number 2 relates to Born-Haber cycle. Iron 2 compounds are generally only stable in neutral, non-oxidizing conditions. It is difficult to determine the lattice energy of FeO experimentally. Use data from the data booklet and this Born-Haber cycle to calculate the lattice energy of FeO in kilojoules per mole. So this is a pretty simple question. We just have to calculate this delta H lattice. They've already given us the formation. This is delta H formation. And they have given us the atomization of iron, right? This is the atomization of iron. Rest of the energies you can just simply find out from the data booklet, right? Like the next energy, this is the atomization of oxygen, which would be bond energy of oxygen divided by 2, and that is 496 divided by 2. Then first ionization energy, which is 156, and first ionization energy, this is 762, and second ionization energy, that is 1560. Then electron affinities are already mentioned. Oxygen first electron affinity, and second electron affinity. And then this delta H lattice we have to calculate. So we just simply have to solve this cycle to get the answer. Now this would be minus 272, heat of formation would be equals to heat of atomization of iron, 416 plus 496 divided by 2, because we are just following the direction of arrows, right? So we just simply have to add them up the way the values we have here. So 496 divided by 2 plus 762 plus 1560 minus, this would be plus minus 141, right? You can see that we have this minus 141. So plus minus 141, that would be minus 141 plus 798 plus delta H lattice enthalpy. And if you just solve this for delta H lattice, the answer would be minus 3915 kilojoules per mole, right? You just have to write the answer here, 3915 kilojoules per mole. All right. So this is simple question. Now next is, most naturally occurring sample of iron 2 oxide are found as the mineral wustite. So woostite has formula Fe20OX. It contains both Fe+2 and Fe+3 ions. Right, it has both Fe+2 and Fe+3 ions. 90% of the iron is present as Fe+2 and 10% is present as Fe+3. So deduce the value of X. So they are saying that in this ore or whatever it is, Fe20OX woostite, it has 90% of iron as Fe2 plus and 10% as Fe3 plus. And in total we have 20 iron here. So what would be the 90% of 20? Right, 90% of 20, that would be 18. So 18 irons would be in the form of Fe+2, and when iron is in Fe+2, oxygen would be in oxygen -2, so formula would be FeO, and we have 18 iron, so that means 18 oxygen. The total number of oxygen we have here is 18, which would combine with Fe2 plus. Now 10% of the iron are present as Fe+3. So 10% of 20 is obviously 2. 20 multiplied by 10%, that is 2, and that means Fe+3 and oxygen -2, so we have Fe2O3. So 2 irons are in the oxidation state of +3 and 18 irons are in the oxidation state of +2. So with +2 we have 18 oxygens, and with +3 we have 3 oxygens. So 18 plus 3, in total we have 21 oxygens. So the value for X is 21. Then next they are saying, state and explain how the lattice energy of FeO compares to the lattice energy of CaO, iron 2 oxide lattice energy compared with the lattice energy of calcium oxide. And lattice energy, you all know this thing, that lattice energy is directly proportional to charge, and lattice energy is inversely proportional to radius, cationic radius. Now charge is similar, right? Fe+2 and Ca+2. So charge is same. Charge is same. So no effect of charge on lattice enthalpy. But we can say that calcium and iron, you can see from the periodic table that both calcium and iron, they belongs to same period, that is period number 4. They belongs to same period, right? And that means that iron would have a smaller, because as we move from left to right in a periodic table, as we move from left to right, the ionic radius decreases. So the ionic radii of Fe+2 would be smaller as compared to the ionic radii of Ca+2. And as ionic radii decreases, lattice enthalpy increases. So we can say that the lattice enthalpy of iron oxide would be greater or larger as compared to the lattice enthalpy of calcium oxide. So the lattice enthalpy of FeO is greater as compared to the lattice enthalpy of CaO because its ionic radius is smaller. All right. Next is heating of FeO results in the formation of Fe3O4 as shown. When we heated iron 2 oxide, we get iron and Fe3O4. Each formula unit of Fe3O4 contain 1 Fe2 plus and 2 Fe3 plus ions. Right, so they are saying that in 1 Fe3O4, there are total 3 iron. 2 of them are in +2 oxidation state and 1 is in +3 oxidation state. Now the question is, show how reaction 1 can be described as a disproportionation reaction. Means same element being oxidized and reduced. I hope everyone knows about disproportionation. So we can see from the equation, on the reactant side, the oxidation state of iron is +2. And when on the product side, the iron which is in elemental state, its oxidation state is 0. So on one side, it is changing its oxidation state from +2 to 0. That means it is getting reduced. And in Fe3O4, now maybe some of you have problem in finding out the oxidation state of iron in Fe3O4. So that's why I'm just solving this here. as the Fe3O4 is a compound, that means sum of the oxidation states is 0. And the oxidation state of oxygen is fixed, that is -2 into 4, this is -8. We have to find the oxidation state of iron, so this would be 3x minus 8, and the oxidation state would be x is equals to 8 upon 3, which would be 2.66. So we can say that the oxidation state of iron is in Fe3O4 is plus 2.66. So on one side it's changing from plus 2 to 0, and on the other side it is changing from plus 2 to plus 2.66. Right, so in here it is being oxidized, and that's why this is a disproportionation reaction. Next is Fe3O4 can be electrolyzed using inert electrodes to form iron. Using inert electrodes to form iron. Obviously, iron would be formed at cathode. To write the half equation for the reaction that occurs at the anode during the electrolysis of liquid Fe3O4. So when we are electrolyzing liquid Fe3O4, that means we have Fe plus 3 ions which move at cathode, and we have oxide ions which moves at the anode. So when oxide ion move towards the anode, the equation would be O2 minus. This will lose electron. In total 4 electrons would be lost, and we get O2. Alrighty, next question is calculate the maximum mass of iron metal formed when Fe3O4 is electrolyzed for 6 hours using a current of 50 ampere. We have to calculate the mass of iron metal that has been deposited on the cathode when a current of 50 ampere is passed for 6 hours. Assume that one Fe2 plus and two Fe3 plus ions are discharged at the same rate, because they have already told us that in Fe3 plus Fe3O4 we have two Fe3 plus ions and one Fe2 plus ion, and they're saying that they are discharged at the same rate, right? So now first we have to calculate the charge, total charge which has been passed. So this would be equals to 50 multiplied by 6 into 60 into 60, right? This is current and this is time converted into seconds. So in total we get the charge 1.08 into 10 raised to power 6 coulombs. All right, now next thing is you can see, as we have this data here, that 1 mole of Fe3O4 contains 2 Fe3 plus and 1 Fe2 plus. So Fe3 plus on cathode, gain of electron occurs. So we have 2 Fe3 plus. That means in total they gain 6 electrons, and we get 2 moles of Fe from Fe3 plus, and we have an Fe2 plus as well, which gains 2 electrons, and we get an Fe. So in totals, how many moles of Fe are we getting? We are getting 3 moles of Fe from 6 moles of electrons, right? And let's just calculate the charge carried by 6 moles of electron. 6 moles of electron, 1 mole of electron carries 96,500 coulomb. So 6 moles of electron, that would be 96,500 coulombs multiplied by 6, and the mass that would be deposited. Mass that would be deposited, we have 3 moles multiplied by atomic mass 55.6, right? Or 55.8, sorry. So this would be equals to 772,000 coulombs, gives 167.4 grams. So when this much coulombs passes, 772,000 coulombs, we get 167.4 grams, and we have charge here 1.08 into 10 power 6 coulombs. So what mass would be deposited by this charge? So we just have to do the cross multiplication, and the answer would be 234.2 grams. Alright, so this is the mass of iron deposited when 50 amperes of current passed for 6 hours. Now the next question is, the next part of the question is, LiFePO4 can be used as lithium-ion rechargeable batteries, right? Can be used in lithium-ion rechargeable batteries, and when the cell is charging, lithium reacts with the graphite electrode to form LiC6. When the cell is discharging, the half equations for the two processes that occurs are as follows. ठीक है जी, this is the discharging. These are the half equations when the cell is discharged. State one possible advantage of developing cells such as lithium-ion rechargeable batteries. Now, this is just, you have to memorize the advantages and disadvantages of these fuel cells and rechargeable batteries like lithium-ion rechargeable batteries. So we can say that this is, it can be recharged again and again. It can be reusable, can be recharged 100 of times, can be recharged hundreds of times. Or we can say that this is more power efficient, You just have to write any one of them. It has low maintenance, right? Low maintenance, and it is more stable or more stable. So these are few advantages of lithium-ion rechargeable batteries. And if they ask you in some question, if they ask you about disadvantages, so what are the disadvantages of this lithium-ion rechargeable batteries? They are fragile, so they need protection, covers. They need protection covers, right? They are expensive. So these are few disadvantages of lithium-ion rechargeable batteries. Now use the cathode half equation. Use the cathode half equation, this one, to determine the change, if any, in oxidation states of lithium and iron at the cathode during discharging. In oxidation states, we have to find the change for lithium. Lithium before reaction at cathode, it has +1 charge. Now 1 electron has been gained. And if you say lithium is gaining electron, so lithium, if lithium gains electron, let's suppose if we say that lithium gains electron, lithium-ion gains electron, it would become Li, neutral, and we have FePO4, which is again neutral. And if both are neutral, there is no way they can form this compound, right? So that means lithium is not gaining electron. Just remember this thing, lithium is not gaining electron, right? So that means which one will gain electron? Fe will gain electron. So lithium, here it has +1 oxidation state, and here it would also have +1. So the oxidation state of lithium is not changing. +1, no change. Iron, before reaction, you can say that FePO4, phosphate ion is -3, so iron would be +3. So iron was +3, and then PO4 gains an electron. And phosphorus, as it is element from 4th period, you can say, right? 3rd period, so that means it has more shell, so it can gain electron. So it would become Fe, when it gains electron, it becomes FePO4 minus, right? So overall charge is now minus, phosphate ion is -3, so iron is now, that means +2. So the oxidation state of iron changes from +3 to +2. Write the equation for the overall reaction that occurs when this cell is discharging. Overall equation. For overall equation, you can say that lithium Li plus would be cancelled with Li plus, electron on reactant side would be cancelled with the electron on product side, and all we left with is LiC6 plus FePO4 makes 6C plus LiFePO4. So this question is now completed. Now third question is, iodates are compound that contains the IO3 minus anion. The IO3 minus anion is shown. This is IO3 minus anion. Explain with reference to the qualitative model of electron pair repulsion, Vesper theory. valence shell electron pair repulsion model, which we studied in AS. Why the IO3 minus anion has a pyramidal shape? Why it has a pyramidal shape? So for pyramidal shape, the central atom must have 3 bond pairs and 1 lone pair. Now, iodine, it belongs to group 7. That means it must have 7 electrons in its outermost shell, right? So let's just count the electrons here. 1, 2, 3, 4, 5. That means it has 2 extra electrons as a pair. So it has now, I hope you all remember this thing, that pi bonds are not being counted while deciding the shape or while deciding the geometry. So we have total 3 bond pairs. 1, 2, 3. Pi bonds are not counted. So we have 3 bond pairs and 1 lone pair, right? 1 lone pair. So that means this is pyramidal shape because it has 3 bond pairs and 1 lone pair. So this is pyramidal shape. The reaction of iodine and hot aqueous sodium hydroxide is similar to that of chlorine and hot aqueous sodium hydroxide. Sodium iodate is formed as one of the products. I hope all of you remembers that equation. So we have to write the equation for iodine with hot aqueous sodium hydroxide. So the reaction of iodine is similar to chlorine reacting with hot aqueous sodium hydroxide. So this would form sodium iodide plus NaIO3 plus H2O. You can just balance this equation. 3, we have 5 and 3. Right, so this is the equation. Next question is the decomposition of hydrogen peroxide is catalyzed by acidified IO3 minus. H2O2 reduces it if acidified IO3 minus as shown. Now this is decomposition of hydrogen peroxide and IO3 minus is being used as a catalyst, right? I hope everyone knows this thing, that when H2O2 decomposes, it gives water and oxygen. So they're saying that IO3 minus is being used as a catalyst. Now H2O2, how it is acting as a catalyst? H2O2 reduces IO3 minus as shown. First, this is being reduced by H2O2 into I2. This is the first step. We can say that this is step 1. Then the reaction is followed by the oxidation of I2 by H2O2. As this IO3 minus is a catalyst, so we have to get this back at the end of the reaction. So what would happen? Once in the step 1, iodine forms, and then this iodine reacts with H2O2. This get oxidized again into IO3 minus, and we have these 3 equations mentioned here. So they have told us this thing, that there are 2 steps involved in this decomposition when IO3 minus is being used as a catalyst. Step 1 is mentioned in the question. Step 2, they have just given us the information about step 2. Now what is they saying? That use the data to show that separate reactions of H2O2 with IO3 minus and with I2, means H2O2 is reacting with both of them, with IO3 minus in step 1 and with I2 in step 2, are both feasible under standard conditions. Feasible under standard conditions means the E0 must be positive, right? E0 or E cell must be positive. In your answer, give the equation for the reaction of H2O2 with I2. Means the second equation, we have to give the second equation. But first, let's just calculate the E0 for the step 1. Now in step 1, you can see that H2O2 is reacting with IO3 minus. So that means this equation would be involved. This equation is being involved because IO3 minus is being used, right? So this equation is being involved, and IO3 minus in this equation is on the reactant side, and in half equation this is also on the reactant side. So that means it is being reduced. It is being reduced into iodine. Now H2O2, that means H2O2 will be oxidized, right? And you can see that in the first equation, H2O2 is on the reactant side. So if H2O2 is on the reactant side, means we cannot use this equation because one of the reactant is already being reduced, so the other one cannot be reduced. The second thing is, you can see that in this equation we have oxygen involved, and there is no oxygen in this equation and no oxygen in this equation. So that means we cannot use this equation. This we have to use because we need IO3 minus. So the second equation which we need for step 1 is this one. First of all, in this equation H2O2 is on the product side, so that means this would get be oxidized, because we have to react IO3 minus with H2O2, right? So if we just calculate the E naught value, this is more positive, so that means this would get reduced, this would get oxidized. So 1.19 minus 0.88, that 0.68, 1.19 minus 0.68, that is 0.51. So that means the reaction is feasible, right? And if you just work out these two equations, you will get this equation mentioned here, right? And then we calculate the let's just write the equation for the reaction of H2O2 with I2. H2O2 with I2. So we have to react H2O2 with I2, and for that we have to take this reaction. First of all, just let me rub this. So for the second step, we have to reverse the equation number 2, this one, because we need I2 on the reactant side. So let's just reverse this one. So this is 1/2 I2 plus 3H2O makes IO3 minus plus 6H plus 5 electrons, right? And the other equation, we need H2O2 will now be oxidizing the H2O2 will be oxidizing the iodine. That means itself it would be reduced. So we have to take equation number 1, because in equation number 1 H2O2 is being reduced. It is on the reactant side. So we will take equation number 1, H2O2 plus 2H plus 2 electrons. This gives 2H2O. Now we have to balance the electrons in both equations. In first equation we have 5 electrons, in second equation we have 2 electrons. So multiply equation number 1 by 2, equation number 2 by 5. So this becomes 1, this becomes 6, this becomes 2, and this becomes 12 and 10, right? So this is 12 and 10, and this would be multiplied by 5. So 5, 10, 10 and 10. Now let's just add these two equations. So 10 electrons are cancelled by 10 electrons. We get 5H2O2 plus I2, 5H2O2 plus I2 plus 6H2O2 on the reactant side, 10H2O2 on the product side. So we left with 4H2O2 on the product side, plus we have 10H plus on the reactant side, 12H plus on the product side. So left with 2H plus on the product side, and 2IO3 minus, nothing else. So 5H2O2 reacts with I2 to give 2IO3 minus plus 2H plus 4H2O2, right? 2IO3 minus plus 2H plus 4H2O2, right? So this is the equation for step 2, and now we have to calculate the E naught values. So this was the reduction value, and this is the oxidation value. So 1.77 minus 1.19, this would be equals to 0.58. Again, this is positive value, so the reaction is feasible, and for 1 we have already calculated. So we just mentioned this on this and this thing on this side as well. right? And for the step 1 we have calculated the E naught value, E cell value 0.51, so this is also feasible. So we just have to find out that both the reactions are feasible under standard conditions. Yes, both the reactions are feasible under standard conditions because the E cell values are positive. Alright, now the next question is, write the overall equation for the decomposition of H2O2 catalyzed by acidified IO3 minus. Overall equation, for overall equation we have to add the step 1 and step 2. So step 1 is 5H2O2 plus 2IO3 minus plus 2H plus makes I2 plus 5O2 plus 6H2. And step 2 is 5H2O2 plus I2 makes 2IO3 minus plus 2H plus 4H2O. This is 4H2O, not 4H2O. Now let's just cancel out whatever is cancelling here. So 2H plus is cancelled with 2H plus, I2 is cancelled with I2, 2IO3 minus is cancelled with 2IO3 minus. So we are left with 5 plus 5, that is 10H2O2, nothing on the reactant side, and we have 6 plus 4, 10H2O plus 5O. And we can just simply simplify it. So this is 5 1s are 5, 5 2s are 10, 5 2s are 10. So this would be 2H2O2 makes 2H2O plus O2. So I hope everyone gets this question. This was a bit tricky one, right? Next is, a student collects some data for the reaction of H2O2 with acidified IO3 minus as shown in the table. Use the data to determine the order of reaction with respect to H2O2, IO3 minus and H plus. Show your reasoning. Order with respect to H2O2. So we have 3 reagents here. First of all, we can take reaction 3 and reaction 4 because IO3 minus is fixed, H plus is fixed, and we can see that the concentration is increased 1.5 times, right, from 0.1 to 0.15. And if you just solve the rate terms here, so this is also increased by 1.5 times. So you can say that with respect to H2O2, this is first order. You can just solve it by yourself. And with respect to IO3 minus, this is 1.5 times and this is also 1.5 times. If you divide this 8.82 by 5.88, you get 1.5 answer. Now for IO3 minus, we can take which two reactions? Let's take reaction 2 and reaction 3. In reaction 2, this is fixed, this is not changing. IO3 minus is changing and this H plus ion concentration is changing, right? So if we double the concentration of IO3 minus, the rate also gets doubled, right? And as you can see, the H ion concentration is decreasing and there is no impact on the rate. So that means with respect to H plus ion, this is 0 order reaction, and with respect to IO3 minus, this is also first order reaction. So with respect to IO3 minus, this is first order, and with respect to H plus, this is 0 order. So use your answers to D1 to write the rate equation for this reaction. You can solve this in detail. I just have written the answers here. So rate is equals to K concentration of H2O2 into concentration of IO3 minus. Alright, now calculate the value of the rate constant K using data from experiment 4 and your answer give the unit of K. So I'm not solving this one, this is pretty simple, I'm just writing the answers here. This is the value of K would be 4.2 into 10 raised to power minus 3, and the unit is mole inverse dm cube second inverse. Next is PbIO3 minus is only sparingly soluble in water at 25 degrees centigrade. The solubility product KSP of PbIO3 minus is this. This is solubility product. Write an expression for the solubility product. So KSP, this is the product of the ions of a partially soluble salt at equilibrium. So this would be Pb2 plus into concentration of IO3 minus square. So calculate the solubility in moles per dm cube of PbIO3 minus. So this is we can say x into 2x square. So that would be 4x cube. So solubility, you just have to find the value of x. So KSP is equals to 4x cube, and the answer of x or solubility is 4.52 into 10 power minus 8. Next question is NH4IO3 minus is an unstable compound that readily decomposes when bound. The decomposition reaction is shown. This is the decomposition of ammonium iodate, and the delta H for this reaction is negative. Use the data in the table to calculate the entropy change of reaction of the decomposition of NH4IO3 minus. So the change in entropy, that is equals to entropy of product minus entropy of reactant, right? So we have the entropy of reactant here 42, nitrogen this would get half because we have this would be multiplied by half, oxygen would also be multiplied by half, and iodine would also be multiplied by half, and you just have to add them up and then subtract it from this one. So the answer would be plus 427. Now the next part is the reaction is feasible at all temperatures. Explain why using the data in F and your answer to F1. Now as you can see that delta H for this reaction is negative, that means reaction is exothermic, delta H is negative, and delta S is positive. And for the feasibility of reaction we use Gibbs free equation, that is delta G is equals to delta H minus T delta S. So if delta H is negative and delta S is positive, so this delta G would always be negative. This would always be feasible. Now next question is the transition elements are able to form stable complexes with a wide range of molecules and ions. State the meaning of the term transition element, which form one or two stable ions with partially filled d subshell. The d orbitals in an isolated transition metal ion are degenerate. In complexes, the d orbitals occupy two energy levels. Complete the diagram to show the arrangement of d orbitals energy levels in octahedral and in tetrahedral. So in octahedral complex, what happens is two of the orbitals move into higher energy level and three are in lower energy level. And in tetrahedral, these three moves into higher energy level and two are in lower energy level. So this is a simple concept. We just have to memorize this thing. Sketch the shape of two d orbitals. One d orbital from the lower energy level in the octahedral complex. So the lower energy level in octahedral complex are dxy, dyz and dzx, means the orbitals between the axes, and this is dx square minus y square and dz square along the axis. So between the axes we can draw any one of them. So let's just draw, let's say this is between the axis, right, and along the axis you can draw this one, or you can draw the dz square as well, which is this one, right? So you can draw any one of them. Now EDDS and EDTA are polydentate ligands that form octahedral complexes with Fe+3. These are polydentate ligands. The formula of the complexes are this and this respectively. On the diagram of EDDS4, this is EDDS4. Circle each atom that forms a bond to the Fe+3 ion in FeDDS-. So circle each atom, that would be this oxygen, 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 oxygen. Nitrogen has a lone pair, so this can also be attached, and this nitrogen, this can also be attached. Now FeDDS minus is red and FeEDTA is yellow. Explain why the two complexes have different colors. Because they generate different energy levels, right? I hope everyone knows the answer, that they generate different energy levels in visible range. So electron require different energy to jump. ठीक है जी. When EDDS4 aqueous is added to Fe3+, the following reaction occurs. We added EDDS in the aqueous Fe3+. State the type of reaction that occurs. What type of reaction occurs? That is ligand substitution reaction. Ligand substitution reaction. Alright. Write an expression for the stability constant K stab. Stability constant K stab. So K stab equation लिखनी है, just simple. This is FeDDS divided by FeH2O6 plus EDDS4 minus, I hope everyone knows this thing, FeEDDS minus upon FeH2O6 3 plus EDDS4 minus. We never write the concentration for water in K stab expressions, right? The table shows the value for the stability constant K stab of both complexes. The values are mentioned for two complexes, FeEDDS4 and FeEDTA. Predict which of this complex is more stable. The one with a higher value of K stab, so obviously FeEDTA is more stable. Explain your answer with reference to K stab, because the value of K stab is higher. When an excess of EDTA4 minus is added to FeEDDS minus, the following equilibrium is established. Because this forms more stable complex, so it displaces EDDS and we get this complex. Calculate the equilibrium constant Kc for this equilibrium using the K stab values given in the table. So the expression of Kc would be equals to the concentration of the K stab value for FeEDTA minus, which is 1.26 into 10 raised to power 25 divided by the K stab value for EDDS, that is 3.98 into 10 raised to power 20. So the answer is 3.16 into 10 raised to power 4. Alright, next question is, carboplatin and cetraplatin are used as anti-cancer drugs. Carboplatin and cetraplatin are used as anti-cancer drugs instead of cisplatin. Okay, we have these two complexes, carboplatin and cetraplatin. Describe the action of cisplatin as an anti-cancer drug. So cisplatin, what it does, it just simply, in case of cisplatin, we have two Cl on this side. So this is cisplatin, Pt, NH3, NH3, Cl and Cl. So these two NH3, they binds with the DNA and they stop the cell replication. So we have 2 marks here. So we just simply say that NH3 on cisplatin binds with DNA and stops cell replication. Right? So it stops cell mutation. Suggest the geometry of the platinum center in the carboplatin complex. So in carboplatin complex, the geometry is that is square planar. Suggests why carboplatin does not show cis-trans isomerism, because in case of carboplatin we have this bidentate ligand which cannot be rotated, so we have one bidentate ligand. Cetraplatin is a neutral complex, right? This is cetraplatin mentioned here. So it's a neutral complex containing the ligands. This one is this and this. So we have ethanoetine, amine, Cl minus, and NH3. Deduce the oxidation state of platinum in cetraplatin. Oxidation state of platinum. So Cl is -1. This is -1. NH3 is 0. NH2 0, oxygen -1, oxygen -1. So overall this is -4. So platinum would be +4 because they're saying this is a neutral complex. So the oxidation state of platinum is +4. Next is compound M is made from 1,3-dimethylbenzene in a 2-step synthesis. Compound M, this is compound M, is made from 1,3-dimethylbenzene. Draw the structure of L. Now L is the intermediary, and as we can see that we have these two methyl groups, and in M we have these two acyl groups. So that means methyl group has been oxidized into carboxylic acid. So the structure of L would be alright. Suggest reagents and conditions for each step of this synthesis. So for step 1, this is oxidation, so acidified KMnO4. Step 2 is we are converting acid into acyl halide, so we can react it with PCl5 and hydrous PCl5 at normal conditions. Write an equation for step 2. So equation for step 2 would be, we have C8H6O4. C8H6O4 reacts with PCl5 and we get C8. Carbon atoms remain same. 2 of the hydrogens would be lost, so that would be H4O2Cl2 plus POCl3 plus H2O. And if you balance this thing, so this will become 2, 2 and 2. Right, this is the equation. Then a student investigates a possible synthesis of M directly from benzene using COCl2 in the presence of an AlCl3 catalyst. Means instead of doing all this thing, if we just simply react benzene with COCl2, we get the compound M as well. So benzene initially reacts with COCl2 as shown. So initially this reacts with AlCl3 complex, the catalyst to get this strong electrophile, and then this electrophile attacks on benzene ring. Benzene reaction 2 is the electrophilic substitution of for H in benzene. So suggest a mechanism for reaction 2. So this is just simply electrophilic substitution reaction. So we have benzene ring reacting with C double bond O Cl plus. So we can say that electrons would be moved here. So we get partial delocalization C Cl, and we have an H here. Then electrons will be moved back into the ring, and we get finally we get C double bond O Cl plus H plus. Alright, so this is the mechanism. Now, fumaric acid is a naturally occurring dicarboxylic acid. This is fumaric acid. Identify the products of the reaction between fumaric acid and an excess of hot concentrated acidified manganate. Products of the reaction. So this is the oxidation of alkene. This double bond would break and we get ethandioic acid and ethandioic acid, because this carbon is connected to one carbon and hydrogen, and this is also connected to one carbon and hydrogen. So we get 2 C double bond O OH, C double bond O OH. So C2H2O4, right? We get 2 moles of this oxalic acid or ethandioic acid. Fumaric acid can form addition and condensation polymers. Draw the repeat units of the addition polymers of polyfumaric acid. Because it has double bonds, it can form addition polymer. So in addition polymerization, what would happen? The double bond would break, and the repeating unit would be simply, instead of double bond, now we have a single bond, CO2H, CO2H, H and H. So this is the repeating unit. Draw the repeat unit of the polyester formed when fumaric acid reacts with ethane 1,2-diol. Ethane 1,2-diol. Right, so we have CH2, CH2OH, OH. This is ethane 1,2-diol. The ester bond should be shown fully displayed. The ester bond shown, right, so we have to draw the repeating unit. So let's say we have this fumaric acid. COH, COH and ethane diol. So what would happen? OH and H would be lost from this side, and H and OH would be lost from this side. So the repeating unit would be C double bond O, C double bond O, O, CH2, CH2, O. This is continuation, right? So this is the polyester that would form. Explain why polyesters normally biodegrade more easily than polyalkenes. Because they can be hydrolyzed. They can be hydrolyzed. Alright, next question is, fumaric acid reacts with cold dilute acidified manganate to form compound P. This is compound P. Diol forms with cold dilute cheminophore. Only 3 stereoisomers of P exist. One of the stereoisomer is shown. Right. Complete the 3-dimensional diagram in the boxes to show the other 2 stereoisomers. So what we can do, we have COOH on this side and COOH on this side, and we just simply put CO2H, CO2H, everything on the same plane, and then just simply reverse the, let's say we call this one 1 and 2. So just simply reverse the OH and H on 1, on first carbon. So this becomes H, OH, and this remains same, H, OH. The other thing we can do, we have reversed this one, this remains same. The other thing which we can do is reverse this one, the second one, this reverses and we get OH, H, and this remains same, OH, H. So this remains same, this get reversed, or we can reverse both, right? So these are the 2 isomers. The enzymes fumarase catalyzes the reaction of fumarate ion with water to form metal ion. This describe with the aid of a suitably labeled diagram how an enzyme such as fumarase can catalyze a reaction. So this is just that lock and key model. I hope everyone can draw the diagram for the lock and key model and explain this one, because this is pretty simple, right? So let's just skip this one. And now next question is, proline is a naturally occurring amino acid. Proline is often found bonded to glycine in a protein. Glycine is NH2 CH H C double bond O OH. Draw the dipeptide proglide. Proglide at OH would be lost from proline and H would be lost from amine, and you get your, I just simply draw it here. So this becomes double bond O, N, H, C, H, H, C, double bond O, OH, and the ring remains same. NH. So this is pro-gly. Alright, next one is name the type of reaction that forms a dipeptide from two amino acids. That is condensation reaction. Proline is able to form a polyproline peptide chain. A section of polyproline chain is shown. This is a polyproline chain, right? This is a polymer. Suggest why the secondary structure of polyproline cannot be stabilized by hydrogen bonding, right? So we all know this thing that secondary structures are stabilized by the hydrogen bonding between the linkages. Now, why it cannot be stabilized? They are saying why it cannot be stabilized. First of all, there is no hydrogen with the NH with the nitrogen, so we can say that no hydrogen with N. Or you can say that we have these bulky groups present, so there would be a huge gap. For hydrogen bonding, we require a set distance, but as we have these bulky groups present, they occupy more space, so that's why it cannot form hydrogen bonds, right? So more bulky groups attached. Alrighty. Next question is the reaction scheme shows several reactions of proline. Write an equation for the reaction of proline with NaOH in reaction 1. This is proline reacting with NaOH. So when this react with NaOH, obviously sodium will displace H, so we get reaction with NaOH. This will produce C4H7NH CO2 Na plus H2O. Then proline has a secondary amine functional group. Secondary amines react with acyl chlorides. For example, dimethyl amine reacts with RCOCl according to the following equation. This is dimethylamine reacting with acyl halide, and we get this link. So suggest a skeletal structure of R, the product of reaction 2. Skeletal structure of reaction R. So when we react it with CH3COCl, so the hydrogen will be lost from this side and Cl would be lost from this side. So we get, I'm drawing the structure here, N, C, double bond O, CH3, rest would remain same, right? This is the structure of R. This is R. I hope you understand this thing. The condensation reaction occurs, H and Cl would be lost, and we get this compound. Alrighty, next is suggest the reagent required for reaction 3. What is happening in reaction 3? Carboxylic acid is being converted into alcohol, so this is reduction. For the reduction of carboxylic acid, we need LiAlH4. Proline was first synthesized in the laboratory using a multi-stage synthetic route. In stage 1, reacts to form a single product U. This reacts with this to form this product U. Name all the functional groups present in the reactants of stage 1. So in stage 1, we have this ester group present, and we have alkene and cyanide. Suggest the type of reaction that occurs in stage 1. So in stage 1, if you see, what is happening here is that this double bond is being broken, and one of the hydrogen from this carbon is attached to this carbon, right? This becomes CH2, and this CH2 has gained the rest of the parts. This is addition. This is electrophilic addition. The type of reaction is, this is electrophilic addition reaction. The one which we studied in alkenes, electrophilic addition. Right? First electrophile adds up, this hydrogen adds up to this carbon, and then the rest of the group would be attached to this carbon. Right? So we have C, this C, then one H, this is one H, and CO2, C2H5 2. This is one CO2, C2H5, and this is another CO2, C2H5. In stage 2, U reacts with reagent V to form W. Stage 2, U reacts with reagent V to form W. Suggest a suitable reagent V. So what is happening here is that cyanide is being converted into amine. So this is reduction, and for this reduction we can use LiAlH4, or we can use tin plus HCl, right? Stage 3 takes place in the presence of an acid catalyst. Stage 3 takes place in the presence of an acid catalyst. X and Y are the only products of this reaction. So X and Y are the only products of this reaction. This occurs in the presence of an acid catalyst. Suggest the type of reaction that occurs in stage 3. So what is happening in stage 3 is, you can see that we have this carbon number 1. Let's say the one which is connected to both CO2, C2H5, we call it carbon number 1. Then we have this carbon number 2, carbon number 3, carbon number 4. Right, so let's say this is the carbon which is connected to CO2, C2H5, carbon number 1, carbon number 2, carbon number 3, carbon number. So this is carbon number 4. This is carbon number 4. This carbon is connected to NH, and as you can see, it has lost one of its hydrogen. So means condensation occurs. So that means either this CO2 C2H5 or this CO2 C2H5 is broken. It's being hydrolyzed. First it converted into acid and alcohol, right? When this CO2 C2H5, just imagine this thing, if this CO2 C2H5 hydrolyzed in the presence of an acid catalyst, it becomes C double bond O OH plus C2H5 OH, and then the C double bond O OH can react with NH2 in a condensation reaction. This will lose hydrogen, this will lose OH, and this will combine with to give us CONH, and here we have this CONH. So means one of the CO2 C2H5 first hydrolyzed and then condensation. The type of reaction that occurs in stage 3, we can just simply say, because we are getting this linkage, so we can see that this is condensation reaction. Deduce the identity of Y. Y we've already deduced. This is C2H5OH. Alright, next question is, after several further stages, Z is produced. So this is Z. In the final stage of the synthesis, Z reacts with a nucleophilic substitution mechanism to form proline. This is proline. Z reacts through a nucleophilic substitution mechanism. Complete the diagram to describe the reaction mechanism of the final stage. Draw curly arrows, ions and charges, partial charges and lone pairs of electron as appropriate. So what happens here is that this nitrogen has a lone pair. This carbon has partial positive and chlorine has partial negative. So nitrogen will transfer its lone pair. This is nucleophilic substitution. Cl would gain this electron. So what would happen is we get this NH2. When this nitrogen shares its lone pair with this carbon atom, we get this bond, right? And Cl is lost. So this is CO2H and Cl is lost. Nitrogen would gain positive charge and we have this Cl negative, and then this Cl would attract hydrogen and these two electrons would move to N, and then we get this final structure. Plus we have HCl, no need to write HCl. just to give you complete information, I have written down here, right? Now identify with an asterisk the chiral center in the proline. So this is the chiral center because this is attached to COOH, NH, this whole benzene ring, and H. Now the next question is, next part is, part of the structure of gelatin is shown. This is the structure of gelatin. Identify the number of amino acid unit in the structure shown. Right, number of amino acids. I mean, we just have to give the number of amino acids. We just have to break this structure from its linkages. So we have this first linkage here, then second one, third one, fourth, fifth, sixth, seventh, eighth. Right, so these are all linkages. Now let's just count the amino acids. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So total 9 amino acids in the structure. At pH 6.5, proline exists in aqueous solution as a zwetterine. Draw the structure of the zwetterine of proline. Explain how the zwetterine of proline forms. So the structure of proline is this one. So in its zwetterine form, this H would be lost by this compound. So the nitrogen would gain the proton. So it would become, I'm drawing the structure here, NH2 plus CO2 negative. Right? This is the, you can say, zwetterine. And we just give the details that the proton would be lost from COOH and NH2 would gain, NH would gain it. The isoelectric point of an amino acid is the pH at which it exists as a zwetterine. 3 of the amino acids in the gelatin are proline, alanine, and glutamic acid. Their isoelectric points are shown. Isoelectric point at which it exists as a zwetterine. So a mixture of these amino acids was analyzed by electrophoresis using a buffer solution at pH 4. Draw and label 3 spots on the diagram of the electrophoregram to indicate the likely positions of each of these species after the electrophoresis. So we are doing this at pH 4. So at the isoelectric point of proline is 6.5. So below 6.5 it would be means in acidic range. So in acidic range, this remains COOH, this gains in hydrogen, so it becomes NH2 plus. So proline would be a positively charged particle. Alanine also has a pH range, has an isoelectric point above 4, so it would also COOH, and this becomes NH3 plus, so this would also be positive. And glutamic acid has an isoelectric point of 3.1, so at pH 4 it would be basic. So in basic medium it loses H plus ions, minus, and this remains NH2. So overall charge -2. So glutamic acid would move towards the positive. Let's suppose glutamic acid would be at here, GLU, glutamic acid, and proline and alanine would move towards the positive, would move towards the negative. And as alanine is the smaller one, so it moves larger distance. So let's suppose here is alanine and here is proline. See, so you just have to explain this thing. Now the next question is, the weak acid ACEs is a compound that can be used to make a buffer solution for electrophoresis experiment. Right, this is the weak acid ACEs. The anion of the sodium salt of ACEs. This is the anion of the sodium salt of ACEs when it loses a proton and combines with sodium. So this is a strong base. A buffer solution is prepared by the following steps. 3.50 grams of this strong base is dissolved in 100 cm cube of distilled water. 50 cm cube of 0.2 mole per dm cube dilute hydrochloric acid is added to the solution. Right, so we have this 3.50 gram of this salt, sodium salt of the weak acid, right? And then we add hydrochloric acid. hydrochloric acid. The resulting mixture is transferred to a 250 cm3 volumetric flask and the solution made up to the mark. So this strong salt, this sodium salt reacts with HCl in a 1:1 ratio stoichiometry. The pKa of aces is 6.88 at 2.98 Kelvin. Calculate the pH of the buffer solution. Now, buffer solution, it forms when a weak acid combines with its conjugate base, और आप कह सकते हैं कि weak acid with its So the buffer solution would form when a weak acid combines with its conjugate base, right? Or we can say the salt. Here the weak acid, here we are adding HCl in the salt, right? So first let's calculate the moles of salt. We have 3.50 grams. So 3.50 grams divided by 204. So we get 0.017 moles of salt, and the moles of hydrochloric acid is 50 into 0.2 multiplied by 50 divided by 1000, that is 0.01 moles of HCl. So when HCl reacts with this salt, let's just assume what would happen. Let's just assume that instead of having this weak acid, we have ethanoic acid, and the salt of ethanoic acid is CH3COONA plus. Let's just assume what would happen when this salt react with HCl. What would happen? We get NaCl and we get CH3COOH, right? So we get our weak acid back. This is our weak acid. So this is what you have to think here, that when we react acid with the salt, we get our weak acid back, right? And what amount of weak acid would we get? We have 0.01 moles of HCl, and the HCl is in 1:1 ratio with the salt. So we get 0.01 moles of weak acid. We have 0.01 moles of weak acid. If 0.01 moles of HCl consumed, we get 0.01 moles of weak acid produced. And the salt we left with, we have 0.017 moles of salt minus, as it is in 1:1 ratio with HCl, 0.01 of it would be consumed with HCl. So we are now left with 0.007 moles of conjugate base, or you can say salt. So now these two would make buffer. Now we have to calculate the concentrations. Divide this by 250 into 1000. 250 divided by 1000 because we have total 250 volume, and this by 250 divided by 1000. So we would get the concentrations, and after getting concentrations, they have given us pKa value. So we can calculate the Ka value from this pKa. pKa is equals to negative log Ka, right? So Ka value would be equals to negative, that would be 10 to the power minus 6.88, taking anti-log, and the answer would be 1.318 into 10 raised to power 1.318 into 10 raised to power minus 7. Now we can calculate the H-ion concentration by using the formula Ka is equals to concentration of H-ion into concentration of salt, which you get from this one, and divided by concentration of acid, which you get from this one. And we have Ka value, we have concentration of salt, we have concentration of acid. You can calculate the concentration of hydrogen ion. And once you get the concentration of hydrogen ion, then the pH can be easily calculated by using this formula. pH is equal to negative log concentration of H plus ion, and your pH would be 6.73, right? So this would be your answer. So this is the last question from this paper.